Hello students, now we will discuss about Ohm's law in this video, and apart from Ohm's law we are also going to do a bit of experimental verification of Ohm's law. Then we are going to discuss in short about ohmic and non-ohmic conductors. Then we will proceed to resistance. Ohm's law, we all know the statement is, at a constant temperature, the current flowing through a conductor is proportional to the potential difference across its terminals. So writing it in mathematical form, current is directly proportional to the potential difference. Now this relation we are going to establish here from the relation of drift velocity. That means we are going to view the microscopic property of a conductor. Now from the previous lesson, you know that drift velocity Vd is equal to minus E by m into tau, where E is the charge on an electron, E is the electric field, m is the mass of one electron, and tau is the average relaxation time. Now, and current also was derived in the previous lesson. The expression for current was Vd En A, where A was the area of cross section of the conductor and N was the electron density. Now replacing this Vd here, since we need an expression connecting I and V, we will just replace this Vd by the previous expression. Vd can be written as minus E by m into tau. This is Vd, and then we have ENA. Rearranging the terms, we will get E square by m. Then we have N left, we have A left, and then we have tau, of course with a negative sign. Now we don't need this E anymore because we need to find an relation between I and E. So what we are going to do is, we will take the potential gradient, where potential gradient, negative of potential gradient is equal to electric field. So we are going to apply this here. Applying that, E will be replaced by minus V by L. So this expression will come out to be V by L. We have M here. Then we have E square N A into tau. So we get a relation between I and V here. And let's see if they are proportional to each other or not. E, electronic charge, is fixed. Electron density is also fixed. Area is fixed. If you don't change the temperature, relaxation time also will be fixed. Obviously mass is fixed, and the length for a given conductor, the length is also fixed. That means all these come out to be a constant. So I will be equal to a constant term multiplied by V. So we can easily conclude I is proportional to V, which is nothing but the statement of Ohm's law. Now from here we will also find an expression for the resistance of the conductor. You know the constant in this statement for Ohm's law is the resistance. Let's rearrange this one. Say it is 1. Let's rearrange 1. We can write V is equal to 1 by K into I. And if we compare it with the expression for Ohm's law, V is equal to Ri. So your R will be equivalent to 1 by K. So here 1 by K is equal to R. So R will be the reciprocal of this K that we have derived here. So this entire term is the K. So R will be 1 by N A E square tau by ml, or R is ml by Na E square into tau. if we write it properly, rearranging, m by n tau E square into L by A. Now here you get one more thing here. You know that resistance of a conductor is directly proportional to the length and it is inversely proportional to the area of cross section of the conductor. That also will be verified from this expression here. Now proceeding to the experimental verification of Ohm's law. We have done this experiment already in our 10th standard. This circuit will be set up here in the circuit. E is the source, that is the battery that we connect to the circuit. K is the key. Right now the key is open. Then we have the rheostat. It is a variable resistance which will help to vary the current in the circuit. This A is the ammeter which measures the current. And here is R, the value of unknown resistance. Later, after the experiment gets over, we can conclude that this R will be a constant. And in parallel to this R, we connect voltmeter which will measure the potential difference. Now how to proceed about the experiment? First you will plug in the key or you switch it on. After switching it on, you will keep sliding the rheostat to various positions. That means you are varying the current. For each value of current, you will note down the value of potential difference. And you will see that from the table that you will be plotting, that as you increase the current, the potential difference also will increase. That means current is directly proportional to the potential difference. On plotting a graph between V and I, we get a straight line. This graph also proves that V is proportional to I, and when you find the slope of the graph, this slope of the graph, you take any point on the graph. Here I have taken these 2 points. I can take these 2 points also to take the slope. Wherever you take the slope, taking whichever points you want, you will conclude that the value of R will always be a constant for a given temperature and the given conductor. That was experimental verification of Ohm's law. But Ohm's law, when it was applied to various type of conductors, not all the conductors were obeying Ohm's law. That means on plotting IV graph, the graph was not found out to be a straight line. For some of the conductors, the graph was a curve like this. Okay. Now the conductors for which you get a straight line graph between I and V, these are called ohmic conductors. Very simple. Ohmic conductors are the conductors which obey Ohm's law. For example, all metallic conductors that we use, then the solutions, electrolytes, that means the solutions in water, all these are ohmic conductors. For them, the graph will be a straight line. Coming to non-ohmic conductors, as the name suggests, these are the conductors which do not obey Ohm's law. Example of non-ohmic conductors are gases. You can see the IV graph for gases here. It is not a straight line. Then we have materials like diodes, triodes. They are conductors, but they do not obey Ohm's law. That means current is not always proportional to potential difference all the time. You can see the graph here. Now, going back to resistance, physically talking, resistance is the obstruction offered by a conductor to the flow of electric current. You know how resistance arises when the electrons collide against each other. They are not able to move smoothly inside a conductor. That is why the obstruction to the flow of current arises. That is called resistance. The formula for which from Ohm's law is V by I. Then we have also derived an expression for resistance which was m by n e square tau into L by A. Then unit of resistance, ohm. If you want to define 1 ohm, you can do it this way. Unit of R will be equal to unit of V by unit of I. Therefore, 1 ohm will be equal to 1 volt per 1 ampere. So, resistance of a conductor is said to be 1 ohm if a current of 1 ampere flows through it when a potential difference of 1 volt is applied across its ends. Now, these ohm, This ohm is the SI unit. What is the CGS unit of ohm? Like we had stat coulomb for charge, we had stat ohm for resistance. That means CGS unit of ohm, CGS unit of resistance is stat ohm. You can see the relation here. You have all noted down in your notebooks also this relation. Now, variation of resistance with temperature. As you increase the temperature or decrease the temperature, what happens to the resistance? You can see the expression here. Everything else is a constant. When now you can see this tau resistance is inversely proportional to the relaxation time. Now what happens when you increase the temperature? The relaxation time decreases. Now when this decreases, obviously resistance has to increase. That means for metals, when you increase the temperature, the resistance will also increase. Now there is a relation which will help you to find out the change in resistance on increase in temperature. So let us have R naught as the resistance of a conductor at 0 degrees Celsius. This will be a constant because resistance of any conductor at 0 degrees Celsius is fixed. Now RT, say you have increased the temperature to 25 degrees Celsius. Now this RT is the resistance of the conductor at 25 degrees Celsius. Now, how does resistance vary with temperature? It is given by the relation RT, resistance at the new temperature, will be equal to R naught, resistance of the conductor at 0 degrees Celsius, into 1 plus alpha into T. Here, the new term alpha that you can see here is the temperature coefficient of resistance. Now, rearranging all this, we can find an expression for alpha. Make alpha the subject. You will find alpha to be equal to RT minus R naught, that is the change in resistance per unit resistance per degree rise in temperature. That is the definition of temperature coefficient of resistance. Its unit, obviously, this will be ohm divided by ohm. They will cancel out each other. T degrees Celsius. So the SI unit of alpha is per degree Celsius. If you look at the value of alpha for metals, it is positive, which means as you increase the temperature, the resistance also increases. For alloys and semiconductor, it is negative. Negative value of alpha implies that on increasing the temperature, the resistance will decrease. That means they will start conducting more on increase of temperature. And there are certain alloys like manganese, constantan, which is used in a meter bridge in the lab. It is 0. 0 means there is no appreciable change in resistance with temperature. That is why they have been chosen as the materials to be used in the meter bridge. You increase the temperature, there is not much change in the resistance. Similarly, you can deduce expression for resistivity. Okay, it is just you have an expression for resistance. This should be known to you. Keep playing with this expression. You will be getting various expressions like resistivity, conductivity. All right. Then you will also be able to understand how resistivity varies with temperature. So you can attempt it to understand on your own. If you have any doubts, kindly let me know.